You've been lied to about the size of this problem, not maliciously, not by anyone with bad intentions, but systematically and consistently in almost every classroom and every popular science article and every well-meaning documentary you've ever watched. The lie is this, that the question of whether life exists elsewhere in the universe is a philosophical question, a matter of speculation, a thing you believe in like you believe in luck or fate or the fundamental decency of strangers. People ask me, and they've been asking me for 40 years, Carl, do you believe in alien life? And every time I hear that word, believe, I have to resist the urge to walk directly out of the building because we're not talking about belief. We are talking about chemistry. We are talking about physics. We are talking about the oldest and most dangerous game science has ever played, which is this: following the evidence wherever it leads, no matter how uncomfortable the destination. And tonight, the evidence has led us somewhere that should make every single person in this room profoundly unsettled and profoundly awake. So stay with me. I'm going to take you somewhere you haven't been before. And I promise you, by the time we're done, the night sky will look different to you than it did when you walked in. Let me start at the beginning. Not the philosophical beginning, not the poetic beginning, the chemical beginning. The actual physical, boring, glorious chemical beginning. What is life? Not what it means, not what it feels like, not why we treasure it. What is it materially in the language of atoms? Life, as best we can define it, is a self-sustaining chemical system capable of Darwinian evolution. That's it. That's the whole thing. A collection of molecules organized in such a way that it can use energy from its environment to maintain and replicate itself and to vary across generations in response to selective pressure. That's a bacterium. That's a redwood tree. That's you. And that definition, which I want you to hold on to very tightly, does not say anything about water. It does not say anything about oxygen. It does not say anything about the temperature having to sit between 0 and 100 degrees Celsius. It does not say anything about Earth, not a single word, because here is what we know about chemistry. It is universal. The same carbon atoms that make up your DNA were forged in the cores of stars that died before our sun was born. The hydrogen in the water in your cells has been around since roughly 3 minutes after the Big Bang. When we point our spectrographs at distant galaxies, we see the same elements, the same molecular signatures, the same physics. The periodic table does not have a local addition. What's true in the Andromeda galaxy is true here, and what's true here is true there. And if chemistry can organize itself into something that eats and breathes and reproduces and fears and wonders on this particular rock, third from an unremarkable star in one of 100 billion galaxies, then we have a very serious intellectual obligation to explain why it couldn't do that somewhere else. And I have never, in 50 years of looking, found a good answer to that question, not one. Now let me show you the scale of what we're actually talking about, because I think most people, when they imagine the universe, imagine something roughly the size of their concept of a lot. They imagine the Milky Way as very large, and it's about 100,000 light years across, and they imagine a lot of stars in it, maybe more than they can count, and they feel impressed, and then they move on. That is not sufficient. Here's the real number. The observable universe, the part we can see, contains roughly 2 trillion galaxies. 2 trillion, not 2 billion, 2 trillion. Each of those galaxies contains, on average, somewhere between 100 billion and 1 trillion stars. Our galaxy alone, the Milky Way, has somewhere between 200 and 400 billion stars. And we have now established through 20 years of extraordinary data from the Kepler Space Telescope and its successors that on average, every single one of those stars has at least one planet. Some have many. The most recent estimates suggest there are roughly 1 trillion planets in the Milky Way alone, and perhaps 40 billion of them orbit in what we call the habitable zone of their star, the region where liquid water could exist on the surface. That's 40 billion planets in one galaxy, in a universe of 2 trillion galaxies. You're probably sitting there thinking, Yes, but habitable doesn't mean inhabited. And you're right. Absolutely right. The existence of a suitable neighborhood doesn't guarantee the existence of a tenant, but this is where it gets strange. And I want you to understand that when I say strange, I mean strange in the most rigorous, uncomfortable, scientifically precise sense of that word. In 1952, a graduate student named Stanley Miller walked into Harold Urey's laboratory at the University of Chicago with an idea. He wanted to know what would happen if you took the gases that were present in Earth's early atmosphere, methane, ammonia, hydrogen, water vapor, put them in a sealed flask and ran electrical discharges through them, simulating lightning, simulating the early Earth, a simulation so crude that Harold Urey himself reportedly told Miller it probably wouldn't work and he should be prepared to be disappointed. 1 week later, Miller opened the flask and found amino acids. Not one, several. The same amino acids that form the backbone of every protein in your body. They had assembled themselves spontaneously from simple inorganic molecules in 1 week in a flask on a laboratory bench in Chicago. And I was 12 years old when that experiment was published. And I want to tell you that it hit me like a hammer. It hit every biologist and chemist and astronomer who understood what it meant like a hammer, because it meant that the basic building blocks of life were not a miracle, they were an inevitability. They were the natural, predictable product of chemistry when you give it the right ingredients and a little energy. And those ingredients are not rare. Hydrogen is the most abundant element in the universe. Carbon, nitrogen, oxygen, they're everywhere. They're the ash of stellar nuclear burning. They rain down from the interstellar medium. We find amino acids in meteorites. We find them in comets. We find the precursor molecules of life drifting in the cold gas clouds between stars, in the dark, in the void, light years from any planet, assembling themselves, because that's what chemistry does when the conditions are right. Now, here's where I have to be honest with you, because this is also where I have been honest with myself, and it has not always been comfortable. The gap between amino acids and a living cell is still enormous. We know amino acids form readily. We know that nucleotides, the building blocks of RNA and DNA, can also form abiotically. We have strong theoretical and experimental reason to think that RNA-like molecules capable of rudimentary self-replication could emerge from the right chemical soup. But we do not yet have a clean step-by-step account of how you get from there to the first true cell with its lipid membrane, its genetic machinery, its metabolic apparatus. We don't have a verified movie of abiogenesis. That gap is real, and I won't pretend otherwise. But here's what I will say. The evidence we have suggests that once the Earth's surface cooled enough to allow liquid water roughly 4 billion years ago, life appeared within a few 100 million years, maybe less. Geologically, that is fast, embarrassingly fast, almost suspiciously fast. It suggests that given the right conditions, the emergence of life is not a fantastically improbable accident. It's what chemistry wants to do. And if that's true here, with this set of ingredients, at this temperature, under this pressure, then the null hypothesis, the starting assumption we should have to work hard to disprove, is that it's happening everywhere those conditions are met. I want to tell you about a conversation I had in 1961 in Greenbank, West Virginia, in a meeting room at the National Radio Astronomy Observatory. There were 11 of us in that room. Frank Drake, who had organized the meeting, was standing at a chalkboard with an equation he had written down almost as a way of structuring the discussion. He was asking how many communicating civilizations might exist in our galaxy. And to get at that number, he broke it down into factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets in the habitable zone, the fraction where life actually begins, the fraction where life becomes intelligent, the fraction of intelligent civilizations that develop technology we could detect, and the average lifespan of such a civilization. We argued about those numbers for 2 days. We didn't agree on much. We still don't. But what we did agree on was this. Even the most conservative estimates gave you a number greater than 1. Even the most pessimistic reading of the evidence said, "You are not alone." That equation became known as the Drake equation, and for decades it was treated by the scientific establishment with a kind of polite condescension. Too many unknowns, they said, too much speculation. And they weren't entirely wrong. Several of the factors were, at the time, genuinely unconstrained. We didn't know whether other stars had planets. We didn't know how readily life originated. We didn't know anything really about the prevalence of intelligent life in the universe. But what has happened in the 60 years since that meeting in Green Bank is that one by one, the unknowns have been replaced by data. And the data consistently has pushed the estimates in the direction of more life, not less. We now know that other stars have planets. We know that some of those planets are rocky, like Earth, and some are in habitable zones, and some have atmospheres. We have detected water vapor and carbon dioxide and methane in the atmospheres of exoplanets. We have found planets orbiting in habitable zones around red dwarf stars, and red dwarfs are the most common kind of star in the galaxy, which means the most common kind of solar system in the galaxy might be the kind with potentially habitable planets. We have found organic molecules in the clouds of gas around newly forming stars, which means planets begin their existence already supplied with the raw materials for biochemistry. Every time we've looked, the universe has turned out to be more amenable to life than we thought. Not less, more. Now, here is where it gets strange. And I mean really strange, because all of this brings us to a problem that has been sitting in the middle of this field like a stone in a road for 70 years, and nobody has driven around it satisfactorily. And I am not going to pretend that I have either. In 1950, Enrico Fermi was having lunch at Los Alamos with some colleagues. They had been talking about the possibility of extraterrestrial civilizations, and at some point during the meal, somewhat out of nowhere, Fermi looked up and said, "But where is everybody?" That question, so simple, so blunt, so devastating, has become known as the Fermi paradox. Here's the argument in its starkest form. The galaxy is roughly 10 billion years old. The time it would take a civilization with rocket technology roughly equivalent to ours to spread across the entire galaxy, even at a tiny fraction of the speed of light, with many thousands of years. Between jumps is something like 10 to 100 million years. That sounds long. It is not long, not compared to 10 billion years. A civilization that emerged just a few 100 million years before us, and there's no reason one would have had ample time to colonize the entire galaxy before Earth even had complex multicellular life. So why don't we see any evidence of that? Why is the sky quiet? Why does every rock on every planet we've looked at show only the signature of dumb chemistry and nobody home? This is the question that keeps me awake at night, not as a rhetorical figure of speech, but literally. I have lain in the dark and thought about this for decades, and I want to be honest with you about the explanations on offer, because some of them are being sold with more confidence than they deserve. Some people say interstellar travel is simply too hard, too slow, too expensive, and no civilization ever bothers. I find this answer difficult to sustain. You only need one civilization in 10 billion years that figures out how to make self-replicating probes. One. And the math takes it from there. Others say intelligent life is profoundly rare. Perhaps we really are the only ones who made it past the single-celled stage. This is possible. It is not something I want to be true, but it is possible. The evolution of complex multicellular life, of centralized nervous systems, of intelligence capable of abstract reasoning. Each of these may be a bottleneck so severe that the galaxy is full of oceans, full of bacteria, and almost nothing else. I think about the Cambrian explosion 600 million years ago, when complex body plans appeared on Earth in what was geologically a blink, but which required billions of years of microbial preparation before the curtain went up. Maybe that setup is commonplace. Maybe the main act is rare. Others say they're there, they're just not talking to us. Because why would they? We've been broadcasting radio waves for about 100 years. That's a sphere of 100 light year radius in a galaxy 100,000 light years across. We have announced ourselves to an infinitesimally small neighborhood. Maybe no one has heard us yet. Maybe they heard us and are watching to see what happens next. I find this possibility oddly comforting, which probably means I should be suspicious of it. And then there is the answer I find most disturbing of all, the one that the physicist John von Neumann and later Frank Tipler and others have raised, and that I think the field has not confronted with sufficient seriousness. What if civilizations that become advanced enough to spread through the galaxy also, almost inevitably, destroy themselves before they get there? What if the great filter is not behind us, not the emergence of life, not the emergence of intelligence, but ahead of us? What if every civilization that reaches our technological level also reaches the capacity for self-annihilation, and most of them don't survive it? I lived through the Cuban Missile Crisis. I worked on nuclear winter. I have sat in rooms with generals and strategists and heads of state who were making decisions about the fate of civilization, and I can tell you without dramatic flourish that this possibility does not seem remote to me. It seems extremely close. And the silence of the sky, if it is the silence of graveyards, is the most important scientific datum we have ever collected. But let me pull back from the edge for a moment, because I don't want to end on that ledge, not yet, and because there's another dimension of this question that most discussions skip over, and which I think is perhaps the most scientifically immediate and underappreciated aspect of the whole problem. We have been talking about life on other planets around other stars. We have been talking about radio signals and interstellar civilizations and the grand sweep of cosmic evolution, but we have an immediately testable hypothesis sitting in our own solar system, and we are, with agonizing slowness, beginning to test it. Mars. Let me tell you about Mars, and what I know about Mars, and what I've known for a long time about Mars. The Viking landers arrived on Mars in 1976. I was involved with that mission. We were looking for life directly. We scooped up Martian soil and ran it through a set of biology experiments designed by some of the best minds in the field, and the results came back ambiguous, not clearly negative, ambiguous. One experiment, the labeled release experiment designed by Gil Levin, gave a positive signal, the kind of signal you would expect from microbial metabolism. But another experiment found no organic molecules in the soil, and without organics, it seemed hard to explain the positive signal as biology rather than exotic surface chemistry. The official conclusion was no life. Levin has spent 40 years disagreeing with that conclusion. I will not tell you he is right. I will tell you he is not obviously wrong, and that the question is not settled in the way that people who have not read the papers carefully sometimes imagine it to be. What we now know about Mars that we did not know in 1976 is this. Mars had liquid water on its surface for billions of years. There are ancient river valleys and lake beds and delta formations of extraordinary complexity. There is evidence of a massive ocean in the northern hemisphere. The chemistry of Martian brines, liquid water below the freezing point due to dissolved salts, may allow liquid water to exist even today. There is subsurface ice, and we have found organic molecules in Martian rocks, complex organics, the kind of molecules that could be precursors to or remnants of biology. We have not found life, but we have found again and again the conditions under which life, by everything we know about life, should have had the opportunity to emerge and to persist. And then there is Europa. I want you to think about Europa, Jupiter's moon, a body slightly smaller than our own moon, covered from pole to pole in a shell of ice. Beneath that ice, we know this now, from the Galileo spacecraft, from the magnetic field signatures, from the tidal heating calculations, beneath that ice is an ocean, a liquid water ocean kept warm by the tidal flexing that Jupiter's gravity inflicts on that moon's interior. An ocean that has probably been liquid for billions of years. An ocean that is in contact with a rocky seafloor where hydrothermal vents may be pouring out chemical energy and heat. An ocean in permanent darkness under 40 kilometers of ice in the outer solar system, a billion kilometers from the Sunday. And on the floor of our own ocean, at the mid-ocean ridge, hydrothermal vents, first discovered in 1977, we found ecosystems of extraordinary complexity and richness. Tube worms, crabs, fish, bacteria, none of which depend on sunlight, all of which are powered by chemical energy from the Earth's interior. If you can have a biosphere at the bottom of the Pacific Ocean running on nothing but heat and chemistry with no connection to the sun, then why not in Europa's ocean? Why not in Enceladus's ocean, Saturn's moon, which is actively venting water vapor and organic molecules into space from cracks in its south pole, like a planetary organism breathing? We have seen those geysers. We have flown through them with the Cassini spacecraft. We have tasted them. They contain hydrogen, methane, carbon dioxide, and complex organics. They have almost everything that the Miller-Urey experiment used to make amino acids. They are spraying it into space for our instruments to analyze. I have to stop here because this is where I made a mistake that I want to tell you about, because it is important and because it cost me something. For many years I was, and I'm choosing this word carefully and cautious. In my enthusiasm for the possibility of life elsewhere, I sometimes conveyed more certainty than the data warranted. I said things on camera and in books that slid almost imperceptibly from the evidence suggests to it is likely to language that, if you weren't listening carefully, sounded like it is so. That was wrong. It was a violation of the contract I have always believed scientists have with their audience. The contract that says, I will tell you what the evidence shows, and I will tell you where the evidence runs out. And I will not paper over the crack between those two things with wishful thinking or poetic language or the desire to make a better story. Carl Sagan, the television personality, sometimes let Carl Sagan, the scientist, down on this, and I think you deserve to hear me say that plainly. The honest position is this: we do not know whether life exists elsewhere. We have extraordinarily good reason to think that the conditions for life are widespread. We have reason to think that the chemistry of life is not exotic. We have reason to take seriously the possibility, the real, physical, scientifically grounded possibility that the solar system contains multiple worlds with the prerequisites for life, and that the galaxy contains billions of such worlds, and that some of those worlds are billions of years older than ours. But we have not found it, not yet, not confirmed. And until we do, intellectual honesty requires that we hold two things simultaneously in our mind: the genuine scientific case for abundance and the genuine uncertainty about whether abundance is real. I want to tell you what it felt like the day we received the first clear image from the Hubble Space Telescope of the Hubble Deep Field, December 1995. The telescope was pointed at a blank patch of sky, a region the size of a grain of sand held at arm's length, and it stared at that nothing for 10 consecutive days. And what came back was not nothing. What came back was 10,000 galaxies. 10,000 galaxies in a grain of sand of sky. I was sitting in my office at Cornell when I first saw that image, and I sat there for a long time without talking, because the image was not just beautiful. The image was an argument. It was an argument that the universe is not a place where life struggles to find a foothold against vast emptiness. The universe is a place of extraordinary abundance and complexity. And the question is not whether it is capable of generating life. The question is whether we are paying enough attention to find it. Let me talk to you about what we're actually doing to answer that question, because I think the gap between the public perception and the scientific reality is still enormous, and the gap is not in the direction you might expect. We have today the technical capability to detect biosignatures, chemical signatures of life in the atmospheres of planets orbiting other stars. The James Webb Space Telescope is doing exactly this right now. It is not speculative. It is not far future. It is measuring the transmission spectrum of starlight filtered through the atmospheres of exoplanets and looking for the chemical fingerprints of disequilibrium, the presence of gases like oxygen and methane together that chemistry alone cannot maintain and that biology could explain. We have not found a definitive biosignature yet, but we are looking with real instruments, with real data, and the sensitivity of those instruments is improving every year. There's a thought experiment I want to offer you, and I want you to think about it seriously rather than metaphorically. Imagine you are an extraterrestrial astronomer sitting on a planet 50 light years from Earth, and you are doing what we are doing, pointing your telescope at promising systems, measuring atmospheric compositions, looking for life. You point your telescope at our solar system roughly 50 years ago, when the light leaving Earth right now was just leaving. You measure Earth's atmosphere. You find oxygen at 21%, wildly out of chemical equilibrium with the surface minerals, which should reduce it quickly without a continuous source. You find ozone protecting a planetary surface. You find nitrogen, carbon dioxide, water vapor. You find methane in the presence of oxygen, which is chemically unstable. The two gases should react and cancel each other out, but they don't because something is continuously producing both. And you also find, if your instruments are good enough, highly specific organic absorption features in the near infrared. You are, from 50 light years away, with entirely passive remote sensing, looking at unambiguous evidence of a biosphere. You have not seen a cell. You have not seen a forest. You have not heard a radio broadcast. You have read the chemistry of a living planet from 50 light years away. That is what we are now capable of doing. That is what is happening right now. The question of life elsewhere is not a question about philosophy or about the limits of our longing for company in the cosmos or about whether we are special. It is a question about chemistry and physics and planetary science and atmospheric dynamics, and it is being answered slowly, painstakingly, by men and women with instruments and patience and a willingness to sit with uncertainty while the data accumulates. I have spent my career in that uncertainty, and I want to tell you genuinely, without the sentimentality that sometimes gets attached to these discussions, that the uncertainty itself is the point. The fact that we don't know is not a failure. It is the most interesting thing that has ever been true. It means the answer is still ahead of us. It means something you do, something some student in this room does, might be the thing that changes that answer. In 1974, I helped compose a message that was beamed from the Arecibo radio telescope in Puerto Rico toward the globular cluster M13, 25,000 light years away. It was 1,679 binary digits, arranged as a rectangle, encoding information about human beings, our form, our chemistry, our location in the solar system, the structure of our DNA. Frank Drake designed much of it. We argued about every pixel, whether it was the right decision, whether we should announce ourselves, whether we were being reckless. We argued about that too, still do. But what I remember most from that day is standing at the base of that enormous dish, looking up at it against the sky, and thinking about the sheer improbability and audacity of what we were doing. A species that has been building cities for 5,000 years, capable of spaceflight for 13, looking out at 25,000 light years of distance and saying, here we are, we exist. We want to know if you do too. That signal will arrive at M13 in roughly 25,000 years, and a reply, if one comes, will reach us in 50,000. I will not be here for the reply. Neither will you. Neither will anyone we know. And we sent it anyway, because the question matters more than whether any individual human lives to hear the answer. That is, I think, the correct attitude toward this problem. Not urgent in the sense of anxious, not desperate for reassurance, not looking for cosmic company because we are afraid of what it means if we're alone, but committed, deeply, stubbornly, scientifically committed to the pursuit of the answer, because the answer, whatever it is, will be the most important thing our species has ever learned. If we find life on Mars, even dead life, fossilized evidence of ancient microbial mats in a billion-year-old rock, then life will have arisen independently twice in one solar system. And if it happened twice here, you would have to be mathematically reckless to insist it happened only twice in a galaxy of 400 billion stars. If we find a biosignature in the atmosphere of an exoplanet, even a probabilistic one, a statistical signal rather than a confirmed detection, we will have taken a census of the cosmos and come back with an answer that changes everything, not just for science, for philosophy, for religion, for the way we raise our children and conduct our wars and decide what we are willing to sacrifice for a future we will not personally inhabit. And if we search and find nothing, if Mars is dead and Europa is dead and the exoplanet atmospheres are pristine and lifeless and every signal we listen for is silence, then that too will be an answer, and a terrifying one. And we will have to sit with it and try to understand what it means. Maybe it means the filter is ahead of us and we should be very, very careful. Maybe it means the emergence of life is genuinely rarer than the chemistry suggests, and we are something close to a miracle which comes with its own weight of responsibility. I do not know which of these futures is coming. Nobody does. But I know which questions to ask, and I know what tools we have to ask them with, and I know that the cost of not asking, of deciding the sky is just decoration, of walking under those 2 trillion galaxies every night without looking up and demanding an answer, the cost of that is not a scientific cost, it's a human one. Look, you came in here tonight with whatever set of feelings you already had about this question. Some of you were already convinced there's life everywhere and wondered why it was taking us so long to confirm it. Some of you were skeptical, inclined to think the vastness of space is vast and empty and that we are alone by default. Some of you were indifferent and came because a friend dragged you. It doesn't matter where you started. What I want you to leave with is not my conclusion. I'm not in the business of handing you conclusions to carry around and repeat. What I want you to leave with is the structure of the argument, the actual evidence, the real unknowns, the genuine stakes. I want you to feel the mass of those 40 billion potentially habitable planets in our galaxy and hold it against the deafening silence we've received from the sky so far and feel the tension between those two things rather than resolving it prematurely in either direction. That tension is not a problem to be solved tonight. It is a research program. It is a civilizational project. It is the biggest question we have ever seriously tried to answer. And here is the thing that I come back to at the end of every lecture, at the end of every sleepless night thinking about this. We are, as far as we can tell, the only things in the known universe that are asking these questions. The only things made of carbon and hydrogen and nitrogen and oxygen that have looked out at the place they came from and wondered whether they are alone in it. That capacity, the capacity to wonder, to build instruments, to ask the sky a question and wait patiently for the answer across decades and centuries, is either the most common thing in the cosmos, distributed among 1 trillion civilizations on 1 trillion worlds, each one looking out and wondering about the others, or it is the rarest thing that physics has ever produced, and we don't know which. We genuinely, provably, measurably do not know. The next person who finds the answer might be in this room tonight. That's not a metaphor. That's not inspiration for its own sake. That's just the fact of where the science is right now and what it needs next. So tell me, what are you going to do about it?